Hello my friends, welcome to part 1, data preprocessing, and mostly welcome to the practical activities of this course. My name is Adlan de Ponteves and I am more than happy to welcome you into this course. We're about to embark on a super huge journey, but yet a very exciting one, because we're going to build together a series of machine learning models from all the branches of machine learning. And now we're about to start part 1, data preprocessing, and this is the first very important step of this journey, because indeed, anytime you build a machine learning model, you always have a data preprocessing phase to work on, right? You have to preprocess the data in the right way so that the machine learning model that you're going to build can be trained the right way on the data. So we have to start with this step. This will not be the most exciting step, but I will make sure to do this very efficiently so that we can rapidly proceed to the branches of machine learning where we're going to build indeed some models. But before that, we have to master data preprocessing, and that's exactly what we're going to do in this part 1. All right, so first of all, make sure that you have the same as what I have on my computer right now. This is the whole machine learning A to Z codes and datasets folder containing all the Python codes and all the R code, as well as all the datasets in each of the practical activities we're going to do together. Let's do this. Let's go inside this part 1 data preprocessing folder, which is structured the following way. It has only one section, luckily for us, so that we can quickly get to the machine learning models. And as any folder in this course, well, it is structured the following way in two folders, first Python and then R. This Python folder contains, of course, all the Python implementations and the dataset, and this R folder contains all the R implementations with the same dataset. So now we're going to go into Python, because each time in each section, anytime we build a model, we're going to start first with Python and then R. Okay, so that if you are more interested in Python, well, you take the first part, and if you're more interested in R, you take the second part. And here I want to say something very important. This course is not meant for you to master both Python and R. We just covered the two tools so that anyone can learn machine learning on their preferred tool. So if you prefer Python, you can just do Python. If you prefer R, you can just do R. And if you want to learn both, well, you're welcome to learn both, but you don't have to. That's what I want to say, okay? So we're going to start with Python here. I'm going to teach you all the tools on data preprocessing, and there you go. That's the files you will find in this data preprocessing folder, in the Python folder. You will first find this data preprocessing tools implementation, which contains all the different tools of data preprocessing that you might have to use on your data sets in order to preprocess them the right way for your machine learning model. Then we have the data preprocessing template, which will be very useful for us to tackle any data preprocessing phase of our future machine learning model implementations in the following parts. So you will see, you will absolutely love this template. And we also have this data in a CSV file, data.csv, which is the data set on which I will show you how to implement all these data preprocessing tools. And just to give you some context, let's say that this data set belongs to a retail company that collected some data from their customers, whether or not they purchased a certain product. So here, each of the rows correspond to different customers, and for each of these customers, well, this company gathered their country, their age, their salary, and whether or not they purchased their product. All right, so that's a simple data set, but I wanted to use a simple one so that we can really focus on all the tools we're going to learn in this section. And speaking of them, well, now I suggest that we start this data preprocessing tools implementation, because indeed this course is really action-based. You're going to learn by doing in this course, and therefore for this implementation and each future implementation, we will re-implement it from scratch. And so there you go, our first implementation will be for all the data preprocessing tools. And now we're going to open this file, and as I explained in the first section of this course, you can either open it in Google Collaboratory by just double-clicking here, or on Jupyter Notebook if you don't like Google Collaboratory. So feel free to select your most comfortable environment. And for Google Collaboratory lovers, well, there we go. Let's open our data preprocessing tools. And first, I'm going to show you exactly the tools that we're going to implement, and mostly that you're going to learn for your machine learning models. So there you go. That's the whole implementation. Let me scroll down a bit. And as you can see, you will get many tools. So let's have a look at them one by one through the table of contents. So the first thing I'll teach you is how to import the libraries. These are the libraries we will always use in any machine learning model implementation, so we will include them in the template so that they can be ready to use for our implementations. Then I will teach you how to import the dataset, that exact same dataset which I just introduced to you a few seconds ago. That dataset, I will show you how to first upload it on Google Colab and then import it in your Python file. All right, so that's the second step, importing the dataset. Then I will teach you how to take care of missing data, because indeed, in most of the datasets you'll work with in your machine learning career, you might encounter some missing data. And that's the case here for our dataset. As you can see, there is a missing salary here and a missing age, and I will teach you exactly what to do in order to handle this. There are some techniques which are the most relevant to then, optimize the training of your machine learning models, and I will show you the best of these techniques. All right, then after taking care of the missing data, I will teach you how to encode categorical data, whether it is the independent variable, which is your predictors, or the dependent variable, which is what you want to predict. So as you can see in our data set, well, we have actually two categorical variables. We have this one, the country column, containing indeed 3 categories, France, Spain, and Germany, as opposed to all these numerical values in the other variables. And also we have this categorical variable containing 2 categories, yes and no. All right, so I will teach you what to do with that situation so that then you can be ready to pre-process any data. After this, I will teach you how to split the data set into the training set and the test set. And that step is very important because each time you want to train a machine learning model, well, you have to create 2 separate sets. One training set where you're going to train your machine learning model to understand the correlations inside your data set, and one test set that you're going to use to evaluate your machine learning models. And that, therefore, on new observations, because the test set, is like new data on which the model wasn't trained. So that's very important to do this in order to check that indeed there is not overfitting, when your machine learning model is trained too well on the training set, so well that it doesn't perform well on new observations. And so that's why this step is very important, and we will include it in the data preprocessing template. And finally, I will teach you a very important tool that you might have to use in some of your machine learning model implementations, which is feature scaling, which actually scales all your features to make sure they are on the right scale. So you won't have to use that all the time. We will see, of course, in each of the machine learning model implementation whether we have to apply feature scaling or not. So you'll have everything, but we have to include this feature scaling tool in the data preprocessing toolkit because indeed we'll have to use it from time to time. All right, that's the table of contents, and we're going to re-implement all this from scratch. However, if you feel you're comfortable with all these tools and you understand them already and you can't wait to move on to the machine learning implementations, well, feel free to just read this code and make sure you understand it 100% and then move on to part 2, regression, where we're going to build our first regression models. However, I really insist that this course must be action-based, so I really want you to take action as much as you can, and that's why if you're ready to do this for data preprocessing, well, stay with me in this part 1 because we're going to re-implement each and every single one of these tools. And to do this, because remember that this Colab file is actually in read-only mode, well, to do this we'll have to create a copy by clicking File here and then Save a Copy in Drive. This will, as you can see, create a copy of this Google Colab implementation on which you will be able to modify and mostly code your own implementation. All right, and that's exactly what we're going to do now. We're going to actually re-implement all these code cells from scratch so that I make sure that you take action, and therefore we're going to remove each one of these code cells by clicking this trash button here, but make sure not to remove, well, the text cells. This is a text cell, this is a code cell, so make sure to only remove the code cells so that we can actually keep this well highlighted structure of this implementation. All right, almost done. A few code cells left. Trash button, trash, 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 and almost done. There we go. All right, so that's the whole structure of this implementation. These are all the tools that you will probably need when pre-processing your future data sets for your future machine learning models. So it's very important that you understand well this implementation. And now we're going to tackle very quickly the very first step of this toolkit, which is the libraries. How to import the libraries, how to have them ready anytime we start building a new machine learning model. Well, there we go. I will show you this right away. It's actually very simple. We're going to import 3 libraries now, which are NumPy, Matplotlib, and Pandas. NumPy will allow us to work with arrays, because indeed you will see that your future machine learning models will expect some arrays as input, and therefore we need a library to work with these arrays, and that's NumPy. Then we'll import Matplotlib, which is the library that will allow us to plot some very nice charts. You will see that we will plot actually many charts and graphs in this course. And finally, Pandas, which will allow us to not only import the dataset, but also create the matrix of features and the dependent variable vector. I will explain, of course, all these concepts later. All right, so let's import these libraries. In order to import a library in Python, it's very simple. You start with import. That's just a command that will allow to import a library or even a function or any type of modules. By the way, a library is an ensemble of modules containing functions and classes with which you can perform some actions and operations. For example, the most well-known library in data science is scikit-learn, and this is a library that contains actually all the machine learning models that you can build by simply creating an object of some classes. So don't worry about all this now. We will see that in great detail each time we build machine learning models. But there you go, you will see that libraries will be super useful for us in order to build our machine learning models. So there we go, import. Then you need to follow by the name of the library you want to import. And the first one we want to import is called NumPy. And then what we usually do is we add a shortcut, because each time we will use a function of the NumPy library, well, we'll have to call first NumPy. And in order to call it faster, well, we can add a shortcut here so that each time we want to call NumPy, we will actually call it with its shortcut. And the shortcut we usually use for NumPy is NP. And as you can see, to add the shortcut, you simply need to add as and then the shortcut name. All right, so each time we will call NumPy, we will actually call NP. Then next library, import. So that next library is Matplotlib. And actually, as I told you, a library is an ensemble of modules, and here we're interested in a particular module called PyPlot, and that's the module that allows us to plot very nice charts. And so here we're not only going to import Matplotlib, but particularly, well, the PyPlot module. And as you can see, in order to get this PyPlot module, I added a dot here, which allows indeed to access the different modules of the Matplotlib library, and the module we chose is PyPlot. And again, we're going to add a little shortcut here, which we're going to call PLT. That's the usual name for this PyPlot module. All right, and finally, we're going to import a final library, which is the Pandas library, a super useful library to pre-process your data sets and mostly to import them. And same for this library, we're going to add the simple shortcut name PT. And there you go, congratulations. Now, not only you know how to import the libraries, but mostly you have your very first data preprocessing tool in your toolkit. So now we're going to move on to the second tool, which will be to import the dataset. Now let's learn together how to import a dataset. As a reminder, we're going to learn how to import the following dataset, data.csv, which is a very simple dataset of, let's say, a retail company that is doing some analysis on which clients purchased one of their products. So the rows in this dataset correspond to different customers of this employee, and for each of these customers we have the country they live in, their age, their salary, and whether or not they purchased the product, okay? So we're gonna learn how to import that CSV on Python using, of course, the Pandas library. Here we go. So let's first create a new code cell, and now let's import this dataset. So the first thing we have to do is to create a new variable, and this variable will contain exactly the dataset. So I always like to choose simple names for my variables, representing well what we're creating. And therefore, since now we're importing the dataset and we want to integrate the dataset in a variable, I'm going to call this variable dataset. Okay, as simple as that. So this variable, what will it be equal to? Well, it will be equal to the output of a certain function by pandas. And this certain function will exactly read all the values of this dataset and will create what we call a data frame. It's a certain format of data, whether it is in Python or even R. So it will create a data frame and it will contain exactly the same rows and columns and values as what you see here. And this data frame will be exactly this dataset variable. All right, so there we go. In order to create this data frame, we're going to call a certain function by the pandas library, which is called read_CSV. And in this function, we will only have to input the name of the dataset with the extension. So since we're about to call a function of pandas, well, the first thing we have to do is call the pandas library. And therefore, remember, since we gave it the shortcut name PD, in order to call it, we need to add here PD. And then to call a function from a library, we need to add a dot. It's always done like that. And that's where you can call the function you want to use. And as we said, this function is named read_CSV, and then you add some parentheses to enter the argument. So there we go, let's do this. This will only what you will have to do when using this read_CSV function. You have to input in quotes the name of the dataset. As a reminder, the name of the dataset is data with a capital D.CSV. So there we go, data.csv. Okay, and this will create the data frame, all the values inside this dataset, and this data frame will be exactly this dataset variable. Okay, so that's the first step, but that's not enough to import the dataset, as a first step of data preprocessing. The next thing that you have to do is create two new entities. The first one is the matrix of features, and the second one is the dependent variable vector. So let me show you exactly what they mean and what they are in the dataset right here. Okay, so I'm going to give you now a very first important principle in machine learning. In any dataset with which you're going to train a machine learning model, you have the same entities, which are the features and the dependent variable vector. Can you guess here what are the features and what is the dependent variable? Well, very simply, the features are the columns with which you're going to predict the dependent variable. And the dependent variable, of course, is the last column, because this company would like to predict if some future customers are going to purchase a certain product based on these informations. So very simply, the features, or also called the independent variables, are the variables containing some information with which you can predict what you want to predict, which is called the dependent variable. All right, so remember this, very important principle. In any machine learning model that you're going to build, you're going to have separately the features, usually in the first columns of your dataset, and the dependent variable, usually in the last column of your dataset. You will see that all the datasets we will use in this course, and most of the datasets you'll use in your machine learning career, will have the same format, with first the features, in the first columns, and the dependent variable vector in the last column. Okay? And so right now, what we want to create, the two entities we want to create are first the matrix of features containing separately these three columns here, country, age, salary, and separately we want to create the dependent variable vector containing only this last column, because that's the column we want to predict. And that's exactly what we always have to do in this first data preprocessing phase. So let's do this. Let's create these two entities, and we're going to call them X for the matrix of features and Y for the dependent variable vector. All right, so let's do this. Starting with X. So how are we going to create X? Basically, that's simple. We have our data set, containing exactly all these columns. And in order to create X, well, we simply have to take the three first columns of this data set, because X will be exactly all these values here, with the three first columns. And so what we're simply going to do is play with the indexes to collect indeed the indexes of these three first columns, basically of the columns of all the columns of the data set except the last one. So let's do this. Let me show you how to do this. First, what you're going to do is take your dataset, that exact same variable which you created in this first line of code here, okay? Dataset. Then from this dataset, and I'm adding a dot here because we're about to use a function, one of the attribute functions of a pandas data frame, and that function is iloc. And what will it allow us to do? Well, as you can see, iLoc here stands for locate indexes, and therefore what this function will do is it will take the indexes of the columns we want to extract from the dataset. Not only the indexes of the columns, but also the indexes of the rows. And actually, we have to start here with the rows. We can specify the rows that we want to get and put into X. And of course, these are all the rows. We want to get all the rows into X. We only want to take the first columns, but we want to keep all the rows. And the trick to take all the rows, whatever dataset you have with whatever number of rows, is to add here a colon. Why is that? Because a colon in Python means a range. And when we specify a range without the lower bound and neither the upper bound, that means in Python that we're taking everything in a range, therefore here all the rows. So that's the trick to take all the rows, and you will always have to take all the rows, so here you won't have anything to change. Then, now we have to specify which columns we want to select with the indexes, and to separate the rows that we just took from the columns, we need here to add a comma. And now we can take care of the columns. Alright, so now I'm going to show you a trick in order to take all the columns except the last one. Because indeed, as I told you, most of the data sets you will use to train your machine learning models will have first the features, in the first columns, and last the dependent variable vector in the last column. So now we're going to use a trick so that we can take automatically, regardless of the number of columns in your data set, all the columns except the last one. Because all the columns except the last one are exactly the matrix of features. And the trick to do that is to add a new range here, which this time will be colon -1. So what does it mean? Well, as we said, the colon here means the range. We know we're taking a range. Here on the left, we have nothing. That means that we're taking the first index, the index 0, because indexes in Python start at 0. And then, we're going up to -1. So what does this -1 mean? Well, -1 means here the last column. -1 in Python means the index of the last column. However, and that's a very important principle in Python which you must absolutely know, a range in Python includes the lower bound, therefore we're including here the lower bound 0, the index 0, but excludes the upper bound. And therefore here we're excluding this index -1, meaning the index of the last column. And therefore, what this will do is it will take all the columns excluding the last one. And that's exactly what we want for our matrix of features X. So voila, there you go. Now you just collected the right indexes to create your matrix of features X. And the beauty of this is that you won't have anything to change when creating the future matrices of features X of your future datasets. But make sure that your future datasets indeed have the features in the first columns and the dependent variable vector in the last column. Okay? Perfect. So in order to finish this line of code, we just need to add here dot values. And this just means that we're taking indeed all the values in all the rows of this dataset and in all the columns except the last one of this dataset. Perfect. So now you're learning a lot. Don't worry if this feels a bit overwhelming at the beginning. I promise you that we will use this trick many, many times, so you will just soon be so familiar with it and master it like a pro. Alright, and now let's do the same for our dependent variable vector. And this will be exactly the same. We'll just have to change one little thing. So I'm going to copy this and paste it right here. And now, according to you, based on what I've just explained, what do we have to change here in order to get the dependent variable vector, which is most of the time, and in our data set indeed, the last column? Okay, so let's see. First, we have to take our data set because we want to extract this last column from our data set. Then we have to use iLoc to collect the indexes of the rows and columns we want. Then we indeed want to take all the rows of the data set because we want to take all the purchase decisions of these customers, whether or not they decided to purchase yes or no the product. So we want all the rows, but then which columns do we want to get here? Well, we only want to get the last column. So according to you, what is the index we need to input here in order to get only the last column? Well, this time, since we only want to get one column, we definitely don't want to get a range. And therefore, I'm going to remove the range here. And then what are we left here? We're left here with -1, and as I've told you, -1 is exactly the index of the last column, so there we go. That's exactly what we need to create this dependent variable vector. And thus, this line of code is done. Congratulations, now you know how to import a dataset, create a matrix of features, and create a dependent variable vector. And the cherry on the cake is that anytime you want to create these for your datasets, you won't have anything to change because this will automatically take all the first columns for the matrix of features and the last column for the dependent variable vector. Alright, so now I'm going to show you indeed that X and Y will be well created. And in order to do this, we're going to add a new code cell here, inside which we're just going to print. So that's the famous print function, which allows you to print anything, whether it is a text or, an array like X or a vector like Y. So we're going to first print X, and then I'm going to add a new code cell here where we're going to print Y. And this is just to show you that indeed X and Y will well be created with this code. Okay, so let's do this. Now, time for the fun part. We're going to execute all these cells here because, so far we've just written the implementations, but we have to run the cells in order to build all this. So let's first run this code cell importing the libraries. All right, so import it. As you can see, if I click here, yes, this one here means it is executed. Now time to run the second one, but before running this, we have to do something very important. It is to upload this dataset here in CSV format inside our Google Colab notebook. And to do this, you just need to click Files here, this little folder, then Upload. Then you're going to go to this whole machine learning A to Z folder containing all the codes and datasets. And inside this folder, you're going to go now to part 1, data preprocessing, in order to get indeed that data CSV file containing the dataset we are importing right now. So open, and now the dataset will be indeed in Google Colab, your notebook, and so now we can run this cell to import it. And there we go, it is already imported, it is executed. So now we're gonna execute this cell in order to print the matrix of features X, just to check that indeed we get all the first columns inside this matrix. And indeed, well, let's check the dataset once again. Remember, the first column is meaning the features we wanted to get into this matrix X are first the country, second the age, and third the salary. These are the 3 columns. And indeed, inside X, we have first the country column with all the countries of these customers, their age, and in the third column, their salary or their estimated salary. So that's perfect. We get indeed the matrix of features X containing all the features, or also called the independent variables. All right, and now let's run this cell to print Y, the dependent variable vector, and indeed it gets the dependent variable vector containing all the decisions whether or not the customers purchased the product, right? We can check no, yes, no, 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 yes, no, no. Okay, so that's in the same order. That's perfect. We now have our dataset, our matrix of features X, and our dependent variable vector Y. And lastly, let me remind why we had to create these 2 entities. That's because the way we're going to build our future machine learning models expects exactly these 2 entities in their inputs. We will use some classes to build these models, and these classes don't expect the dataset as a whole, but these 2 separate entities. And that's the only reason why we had to create these 2 separate entities. So now you know, and therefore, congratulations. Not only you improve your knowledge of machine learning, but also you now know how to import a dataset and create a matrix of feature and a dependent variable vector. So now we're going to proceed to the next step, which is a new tool which I'm going to teach you, and that is taking care of missing data. Indeed, as you can see, the dataset contains some missing data right here. You can see this is an empty cell. So I will teach you exactly how to handle that case, which happens most of the time in datasets. So let's do this in the next tutorial, and until then, enjoy machine learning. Okay, my friends, so now let's add a new tool to our data preprocessing toolkit, which is taking care of missing data. So indeed, if we have a look again at our dataset, data.csv, we notice that there is a missing salary here for this specific customer from Germany of 40 years old and who purchased the product. So Generally, you don't want to have any missing data in your dataset for the simple reason that it can cause some errors when training your machine learning model, and therefore you must handle them. There are actually several ways to handle them. A first way is to just ignore the observation by deleting it. That's one method, and this actually works if you have a large data set and if you have only 1% missing data, removing 1% of the observations won't change much the learning quality of your model, so 1% is fine, but sometimes you can have a lot of missing data and therefore you must handle them the right way. So that was the first way, to ignore them, to remove them. And now a second way, and this is what we're adding right now in the toolkit, is to actually replace the missing data, the missing value, by the average of all the values in the column in which the data is missing. So here we have a missing salary. What we want to do is to replace this missing salary by the average of all these salaries. This is a classic way of handling missing data, and I'm going to teach it to you right away. So here we go, taking care of missing data. Let's create a new code cell and let's replace that missing salary by the average of all the salaries here. All right, so to do this, we're going to use the libraries, and actually I'm about to introduce you to one of the best data science libraries. I'm talking about scikit-learn. Scikit-learn is an amazing data science libraries containing a lot of tools, including a lot of data preprocessing tools. You will see that we will actually use scikit-learn a lot in this course. More than half of the machine learning models we will build in this course will be built with scikit-learn. So if you don't know scikit-learn yet, I'm telling you, you're going to absolutely love it. And so for the first time here, we're going to use scikit-learn to handle missing data. And to do this, the class that we're going to use from scikit-learn is called simple inputter. We're actually going to first import that simple inputter class. Then we will create an instance, an object of the simple inputter class. This object will allow us to exactly replace this missing salary here by the average of the salaries, and then we will have an updated dataset, an updated actually matrix of features, because we will apply this inputter on the matrix of features only. So we'll have a new matrix of features with no missing data, because the missing salary will have been replaced by the average salary. All right, let's do this. Perfect. So first, since this class belongs to scikit-learn, well, we're going to start here by going from scikit-learn, which has the name sklearn. So sklearn, then remember, in order to access a module, we have to add a dot, because actually this simple inputter class which we want to import belongs to a certain module of scikit-learn called impute. This one, impute. And from this impute module, well, we're going to import, there we go, the simple inputter class. See, Google Colab really assists you well. Simple inputter class, perfect. Then next step, as I said, the next step is to create an instance of this class, which you can exactly see as the tool itself. The tool that you'll use to replace that missing salary by the average of salaries. So since we're about to create a new object, well, we have to introduce here a new variable, and we're going to call this variable inputter. Okay, inputter, which will be exactly this object of the simple inputter class. And therefore, since it will be the object of the simple inputter class, well, we have naturally to call this class simple inputter. So I'm going to copy this and paste that here. That's how you create an object of the class. You simply call the class, then you add some parentheses, and there you go. Now you're going to enter the right arguments in order to replace indeed this missing salary by the average of salaries. Because note that there are actually many replacements that you could do. You could, instead of replacing it by the average salary, you could replace it by the median salary. There is a difference between the average and the median. You could also replace a missing value by the most frequent value, right? That would be, for example, relevant for categories. Okay, so you have many options, but the most classic one and the one option that I recommend is the average salary, the mean salary. Okay, and so that's exactly what we have to enter here. First, we have to specify which missing values we have to replace, and so that's why we have to enter here first argument called missing values, which has to be equal to np, the numpy library .nan, and that's just to say that we want to replace all the missing value in the dataset, like this one. This is like an empty value. This is what this means, an empty value. And then the second argument we have to input here is exactly the one saying that indeed the missing values here, the empty values of the dataset, will be replaced by the mean. And to do this, we have to add the next argument here, which is strategy. And this argument will be equal to, in quote, mean. Okay? And that's just to say that we want indeed to replace all the missing values in the matrix of features by the mean of the feature itself. Okay? Then, almost last step. Now, remember, this is just an object. We haven't connected anything yet to our matrix of features. So the next step is indeed to apply this inputter object on the matrix of features. So how are we going to do that? Well, remember that a class contains an ensemble of instructions, but also some operations and actions which you can apply to other objects or variables. And these are called methods, they're like functions. And one of them is exactly the fit method. The fit method will exactly connect this inputter to the matrix of features. In other words, what this fit method will do is it will look at the missing values in the salary column, and also it will compute the average of the salaries. All right, so that's simply what it will do. And then that will not be enough to do the replacement we want. To do the replacement, we'll have to call another method called transform, and which will this time apply the transformation, meaning it will replace the missing salary here by the average of the salaries. Okay, so let's do this. Let's first call the fit method. In order to do this, well, of course, we have to call first our object, inputter. And then from this object, adding a dot, we will call the fit method, which has some parentheses because it's like a function inside a class. And what does this function expect as argument? Well, it simply expects all the columns of X with numerical values, but only the ones with numerical values, not the ones with text or strings or categories. And so, well, how do we get this column? Well, first, let's get the matrix of features X, because that's where we want to replace the missing data. And from this matrix of features X, well, first we're going to look at all the rows. This fit method will read the whole column that we specify inside this fit method. But then for the columns, here, we could specify all the columns where to look for some missing data. However, this first column has danger. It is a column with strings, and therefore this might cause a warning or an error when looking for some missing data here. Therefore, we're only going to specify these columns with only real numbers, age and salary. And therefore here, we're going to enter the range from 1 to, be careful, not 2, because remember, the upper bound of a range in Python is excluded. So if we exclude 2, this will exclude the salary. Therefore, we have to go up to 3. Okay, up to 3. So that, well, this fit method will look for all the missing values in the age column and the salary column. So here we're specifying specific columns, which are the age column and the salary column. And that's because we know that there is a missing salary. And by the way, there is also a missing age. However, I recommend on a general rule to select all the numerical columns, because in your career, you will actually work with huge data sets and you won't be able to see where the missing values are. So just include all the numerical columns to make sure to replace any missing data. Remember to exclude these ones, the string columns. Okay, so that's just something important to consider. And then here we go. This will connect our inputter to our matrix of features. And now, final step, we have to call the transform method, once again from our inputter object. And so this transform method will exactly do that replacement of the missing salary here by the mean of the salaries. And same for the missing age, it will be replaced by the mean of all the ages in the age column. And so according to you, what do we have to input here? Well, there is no trap here. We of course have to input the columns of X where we want to replace missing data. And so these are the age column and the salary column. And therefore, we simply have to input exactly the same as what was input in the fit method. So we're just going to take this, copy this, and paste that inside the transform method. However, be careful, this transform method actually returned the new updated version of the matrix of features X with the two replacements of the missing salary and the missing age. And therefore, what we want to do now, and that's the last thing we have to do, is to indeed update our matrix of features X. And to do this, well, since this exactly returns these two columns here with that replacement done, well, what we want to do to update X is actually to take this, take the second and third column of X, matrix of features, and change it by what will be returned by this transform function of the inputter object, so that the second and third columns of X will be replaced with that average age and average salary, and therefore the whole matrix of features X will be exactly the same, but with these new average age and average salary. Okay, we're going to check that right away now. To do so, we're going to create a new code cell where we're going to print the new matrix of features X, and let's see if indeed that missing value that we can clearly see here as, once again, NaN, is replaced in this new version of X. So let's not forget to run these two cells here, this first cell to indeed replace the missing data, and now this cell to print the new matrix X. And there you go, as we can clearly see, that missing salary in the previous matrix of features X was indeed replaced by the average salaries of this column. Okay, check that if you want, but there you go. Now you have another tool in your data preprocessing toolkit, so congratulations. And now we're going to proceed to a new tool, which is to encode categorical data. All right, my friends, let's do this. Let's proceed to the next tool in our data preprocessing toolkit, which is about encoding categorical data. So first, let me explain why we have to do this. Let's open the dataset again. And as we can see, this dataset contains one column with categories, France, Spain, or Germany. First, you might guess that it will be difficult for a machine learning model to compute some correlations between these columns, the features and the outcome, which is the dependent variable. And therefore, of course, we'll have to turn these strings, these categories, into numbers. So one idea would be to encode France into 0, Spain into 1, and Germany into 2. However, if we do this, our future machine learning model could understand that because France is 0, Spain is 1, and Germany is 2, there is a numerical order between these three countries, and mostly it could interpret that this order matters. Whereas, of course, it is absolutely not the case, right? There is not a relationship order between these three countries, France, Germany, and Spain. So we want to avoid the model to have such an interpretation, because that could cause some misinterpreted correlations between the features and the outcome which we want to predict. Therefore, we can actually do much better than just encode these three countries into 0, 1, and 2. And this thing that we can do better is actually one-hot encoding. And one-hot encoding consists of turning this country column into three columns. Why three columns? Because there are actually three different classes in this country column, three different categories. If there were, for example, 5 countries here, we would turn this column into 5 columns. And one-hot encoding consists of creating binary vectors for each of the countries. Let me explain this right away. So very simply, France would, for example, have the vector 1, 0, 0, Spain would have the vector 0, 1, 0, and Germany would have the vector 0, 0, 1. So that then there is not a numerical order between the three countries. Because instead of having 0, 1, and 2, we would only have zeros and ones, and therefore 3 new columns. I'm going to show you, of course, what we're going to create. We're basically going to replace this country column by 3 new columns containing the zeros and ones encoding each of the countries. That is called one-hot encoding, and that is a very useful and popular method to use when preprocessing your datasets containing categorical variables. So that's the first thing we'll do here for this country column. And then remember that there is also this purchased columns that has labels, non-numerical values with yes and no's, and we will actually have to replace them by zeros and ones. And that's totally fine for the dependent variable as long as it is a binary outcome. It is super fine. It will actually not compromise the future accuracy of the model if you just replace no and yes by 0 and 1. Okay, so I will teach you how to do these two things. And first, let's start by one-hot encoding the country column here. And there we go. let's create a new code cell for this new step, encoding the independent variable. Alright, so to do this, we're going to use two classes. The first one is the column transformer class from the compose module of, once again, the scikit-learn library, and the second class is the one-hot-encoder class from the preprocessing module of the same scikit-learn library. So first, let's import these two classes. So we have to take them from scikit-learn, from which we're going to call first the compose module, there we go, from which we're going to import that class we're interested in, which is, as Google Colab guesses perfectly, column transformer. And then from scikit-learn once again, we're going to get access to the preprocessing module, perfect, from which we're going to import the one-hot-encoder class. And now we're going to mix these two classes in order to do this one-hot encoding on the country column. So let's do this. You cannot actually really guess how we're going to do this. So let's implement the solution together. The first step is to create an object of the column transformer class, and therefore we're going to create a new variable here which I'm going to call CT, which stands for, the object of the column transformer class. So CT equals, and now of course remember, to create an instance or an object of a class, you have to call the class itself. So column transformer class, there we go. Now since it is a class, we have to add some parentheses, inside which we have to enter two arguments. So these two arguments are first transformers, where we will specify what kind of transformation we want to do and on which indexes of the columns we want to transform. And the second argument is remainder, which will specify that we actually want to keep the columns that won't be applied some transformations, meaning age and salary. So let's do this. Let's first enter the names of these two arguments. The first one is transformers. There we go, this one, transformers. I'm going to add a colon here, and then let's just add the next one, and then we'll input them. The next one is remainder. This one, exactly. And now let's input them. So for the first one, transformers, we actually have to specify three things. First, the kind of transformation, which is encoding. Second, what kind of encoding we want to do, which is one-hot encoding. And third, the indexes of the columns we want to encode, meaning country, the country column. So we have to actually input all that in a pair of square brackets and then some parentheses. So that's just the format expected by this transformers argument. We're actually going to enter here a tuple, of three elements inside these parentheses. The first element is, as we said, the kind of transformation, and to specify that we want to do some encoding transformation, we have to enter here in quotes encoder. So that's the first element. Then second element, we simply have to enter the exact name of the class that will proceed to this encoding. So I'm going to copy this because this is going to be exactly the second element expected here. And I'm adding some parentheses because that's a class. And finally, the third element inside this tuple of parentheses is, in a pair of new square brackets, the indexes of the columns we want to apply one-hot encoding. We want to transform. And so these indexes, of course, are only one index. It is the index of the country column. The country column is the first column of our matrix of features. And remember that in Python, indexes start at 0. Therefore, this country column has index 0. And that's what we have to enter here, only 0. All right, so that's all good for the first argument here, transformers. The transformers argument is equal to all this, in square brackets. So great. And now the second argument, remainder. So here we want to specify in quotes the following code name, which is pass through, and which is a code name that will say that we indeed want to keep the columns that won't be applied some transformation, that won't be one-hot encoded, which are of course age and salary. If we don't include this remainder equals pass-through here, then when we apply the transformation on X, we will only keep, the first three columns resulting from one-hot encoding. And of course, we want to keep age and salary into our matrix of features. That's what it's used for. Okay? So good. Now we have our CT object. It is of course not connected yet to our matrix of features X, and so that's exactly what we want to do. But there is actually some good news. This time we don't have to do it in two steps, by first calling a fit method from the object to connect our object to the matrix of features X and then apply as a second step the transform method to apply the transformation. No, this time we can do it at once because our column transformer class actually has a method called fit transform, which will do exactly the process of fitting and transforming at once, at the same time, So that's perfect. Let's use this. And to use this, well, of course, we have to call first our CT object, from which we're going to call this fit transform method, which will get as input, well, of course, X, because that's what we want to transform. We want to transform the matrix of features X inside which we want to one-hot encode the country column. Perfect. So now two things to understand. Well, first, this fit transform method will, of course, return as output the new matrix of features X with the three columns, one hot encoding the country column. And therefore, since that's exactly what we want to get as the new matrix of features X, well, we're just going to update this new matrix of features X. So that's why I'm adding here X equals the result, the output of this fit transform method. But then we have to do one more thing, which is related to the fact that the fit transform method actually doesn't return the output as a numpy array, and it is absolutely compulsory to have X as a numpy array because this will be expected by the future machine learning models which we're going to build. In order to train the future machine learning models, where we're going to use a train function, which is actually called fit, and this train function will expect the matrix of features X as a numpy array. So here we want to force the output of this fit transform method to be a numpy array, and to do this we simply need to call, well, numpy first, which has a shortcut name np, from which we're going to call this array function, which will take as input exactly the output of the fit transform method. All right, so now all good. Now we apply correctly this transformation to one-hot encode the columns of this matrix of features X. Let's check that right away by creating a new code cell and then printing this matrix of features X. There we go. Now let's run this cell and then running the next one. And what do we see? Well, we see exactly what was expected here, meaning that we no longer have the first country column with the text, the three countries here in strings. This time we have, as we said, three new columns. So I don't know if you can see it well, but that's the first one, that's the second one, and that's the third one, where each row encodes one of the three countries. So actually France, that was the first row. France is encoded as 1, 0, and 0, a vector of 1, 0, and 0. Then Spain is encoded as a vector of 0, 0, and 1, and Germany is encoded as a vector of 0, 1, and 0. You see the unique idea for each of these three countries thanks to these three columns here. And that's exactly the idea of one-hot encoding. We not only turn our countries into numerical values, but also there is not a numerical order thanks to these 0 and 1s here in three columns. So that's perfect, and that will provide the best results for our future machine learning models. All right, so congratulations. Now you know how to one-hot encode some categorical data. Now we're going to quickly do another encoding for the dependent variable because indeed it has a text format, no and yes, and we would just like to convert these strings into 0 and 1 respectively. And to do this, well, that's very simple. We're going to use another class called label encoder, and which will exactly encode these no's and yeses into 0s and 1s respectively. All right, so let's do this. Let's create a new code cell here. Let's scroll down a bit. Here we go. And now let's encode the dependent variable. So as we said, we're going to use the label encoder class, which we get from the scikit-learn library again, from which we're going to call the preprocessing module, from which we're going to import, well, there we go, the label encoder class. Then, exactly as what we did before, we're going to create an object of this class, which we're going to call LE. And to do this, well, we simply need to call the class label encoder. There we go. Then some parentheses. Then good news, we don't have to input anything in the parentheses because, we will just need to enter directly y because it is only one single vector. So it will be obvious what will be needed to encode. And so there we go. Let's do this. let's first call our object LE, from which we're going to call, well, good news once again, there is a fit transform method, which we can call directly on Y, and which will exactly convert the no's and yeses, the text inside numerical values. And this time we don't have to have a numpy array because this is the dependent variable vector. It doesn't need to be a numpy array, as what is expected by the future machine learning models. So we can just set the new Y to be what is returned by this fit transfer method applied to the old Y with the texts no's and yes. All right, let's check this. Let's create a new code cell just to print our dependent variable vector Y. Let's run this cell first and then this one, and let's see if we get zeros and ones. And yes, indeed, we get the zeros and the ones, right? No corresponds to 0, and then 1 here corresponds to yes, right? Then it should be 0, 0, 1, 1, 0, 0, 0, 1, 1, 0. Okay, so all good. So now you not only know how to apply one-hot encoding when you have several categories in one of the features of your matrix of features, but also you can do a simple label encoding when you have, two classes, which you can directly encode into 0 and 1, a binary outcome. All right, perfect, congratulations. Now you have an extra tool in your data preprocessing toolkit, the way to encode categorical data. And now we're gonna move on to the next tool, which will be to split the data set into the training set and the test set. And now we have two tools to cover. The first one being splitting the data set into the training set and the test set, and the second one being feature scaling. So before we start, I'm about to answer one of the most frequently asked questions in the data science community, which is, be ready for it, do we have to apply feature scaling before splitting the dataset into the training set and test set, or after? I've seen this question many times, and you will find that question in many forums of the data science community. Some people will say that we have to apply feature scaling before the split. Some people will say after the split. And now I'm about to reveal the right answer. There is only one right answer, which is, by the way, totally obvious after you get the explanation. So the answer is we have to apply feature scaling after splitting the dataset into the training set and the test set. And now let me explain. So first, just to make sure everybody understands, let me explain the what first, and then I'll explain the why. So, of course, splitting the dataset into the training set and the test set consists of making two separate sets. One training set where you're going to train your machine learning model on existing observations, and one test set where you're going to evaluate the performance of your model on new observations. And it's important to understand that these new observations are exactly like, some future data that you're going to get and on which you're going to deploy your machine learning model. All right? So that's this first tool. And now, feature scaling simply consists of scaling all your variables, all your features actually, to make sure they all take values in the same scale. And we do this so as to prevent one feature to dominate the other, which therefore would be neglected by the machine learning model. All right, so that's the what for both of these tools. Now, let me explain the why we have to apply feature scaling after splitting the data set into the training set and the test set. It's really obvious. It is for the simple reason that the test set is supposed to be a brand new set on which you're going to evaluate your machine learning model. So it's exactly like, you're training your machine learning model on your training set, and then later on, after it is trained, you're going to deploy it on new observations. So what this means is that the test set is something you're not supposed to work with for the training. And feature scaling is, as you will see, a technique that will get the mean and the standard deviation of your feature, in order to perform the scaling. So if we apply feature scaling before the split, then it will actually get the mean and the standard deviation of all the values, including the ones in the test set. And since the test set is something you're not supposed to have, like some future data in production, well, applying feature scaling on the original data set before the split would cause some what we call information leakage on the test set. We would grab some information from the test set which we're not supposed to get because it is supposed to be new data with new observations. So remember this, the essential reason why you should not apply feature scaling before the split is to prevent information leakage on the test set, which you're not supposed to have until the training is done. Alright, so I think I've explained enough. Now, we're relieved that at least it's 100% clear for everyone. And so there you go, my friends. Let's implement one of the last tools of this data preprocessing toolkit, which is indeed the split of the dataset into the training set and the test set. Alright, so how are we going to do this? Well, we're going to do it with a function by scikit-learn, you know, the most popular and useful data science library, because once again, this library contains a module that is called model selection, which contains itself a function called train test split. And this function will exactly do what we want, which is to create 4 separate sets, actually not 2, but 4, because we will actually create a pair of matrix of features and dependent variable for the training set, and another pair of matrix of features and dependent variable for the test set. Alright, so we're basically going to get 4 sets, xtrain, which is the matrix of features of the training set, xtest, which is the matrix of features of the test set, ytrain, which is the dependent variable of the training set, and ytest, which is the dependent variable of the test set. That's exactly what we want. And now, why do we want this? Well, it's not us, it's actually the future machine learning model that we will build in the next part, which will be all of them expecting this format as input. You know, for the training, it will expect xtrain and ytrain as input in a method actually called the fit method. And for the predictions, also called inference, these models will predict xtest. All right? So that's the reason. It is simply the format expected by the future machine learning models. And now let's get these 4 sets. So we're going to get them from scikit-learn, of course. There you go. From which we're going to get access to model selection. I really like Google Colab. And then from which we're going to import that train underscore test split function. Perfect. You see how we can be so efficient thanks to the assistance of Google Colab. I hope you really like it as well. All right, so now that we have this function, well, we're going to use it. And since we already know what this function will return, as I've just explained, well, let's create these 4 variables returned by this train test split function. And as we said, they are first xtrain, the matrix of features of the training set, therefore containing all the countries, one hot encoded, ages and salaries of the training set. So xtrain, then xtest, the matrix of features of the test set, then ytrain, which is the dependent variable of the training set, meaning all the purchased decisions of the customers in the training set, ytrain, and then ytest, which same contains all the purchased decisions of the customers in the test set. All right? So that's the 4 variables returned by this train test split function. And since it is the function that returns this variable, well, let's take that function right away and let's add here an equals and train test split and then some parentheses. And now the question is, what do we have to input inside this function? All right, so actually there are some parameters that we can guess, right? Because indeed, this train test split is supposed to split something. So one of the input will be that something which we're about to split and which is of course our dataset. However, of course, this function does not expect the dataset as a whole. It expects, well, the combination of the matrix of features x and the dependent variable vector y. And that's the first 2 inputs of this function. So let's input them here. X first, the matrix of features, and y, the dependent variable vector. Great. Y, yes, then comma, and then next argument. So we still have to input 2 more arguments, which are going to be first the split size, you know, because we're not going to split this data set into a training set and a test set of the same size. Actually, we need a lot of observations in a training set and a few in the test set, but we need a lot of them in the training set so as to give the future machine learning model more chance to understand and learn the correlations in the data set. So let me just tell you the recommended size of the split. Well, I recommend to have 80% observation in the training set and 20% in the test set. All right, this is a very good split, and therefore here we're going to input a new parameter which is test size, and we'll set that equal to 0.2, right? 20% observations will go into the test set. And therefore here, since we have 10 observations in this data set, that means that 8 observations will go into the training set, meaning 8 customers will go into the training set and 2 in the test set. And this is not necessarily the last 2, they will be taken randomly, but 8 of them will go into the training set and 2 in the test set. All right? And now we'll add one final argument just for teaching purposes so that we can have the same results displayed in here, in the notebook, because then I'm going to run some prints to show you these 4 elements returned by this train test split function, the training set and the test set. And since there are some random factors that are going to happen during this split, right, because the observations will be randomly split into the training set and the test set, well, to make sure we have the same random factors, we'll just add here random state equals 1, right? We're just fixing the seed here so that we'll get the same split and therefore the same training set and same test set. All right? And that's it, right? This is the code to split the data set into the training set and the test set. Let me zoom out a bit so that you can see it. All right, so that's the full code. This will return indeed these 4 new sets composed of the training set in Xtrain and Ytrain and the test set in Xtest and Ytest. Let me show you this right away. So we're going to add 4 new code cells here, right? And we're going to print each of these created sets. So first we're going to print Xtrain. Let me copy this. Then we're going to print Xtest. Then we're going to print Ytrain. And finally, we're going to print Ytest. Perfect. All right, so now let's execute everything, starting with this cell here, splitting the data set into train set and test set. Done. Perfect. Run successfully. Now let's run the cell to print Xtrain. And as you can see, indeed, we have now 8 observations in this training set, right? 1, 2, 3, 4, 5, 6, 7, 8, which correspond to 8 customers taken randomly from this data set. And we clearly recognize the features here, with first the 3 columns being the one-hot encoded variables that encode the country categorical variable. We also call that dummy variables. Then we clearly have here the age as the second variable, as the second feature, and then the salary. So we clearly have a great matrix of features for the training set. All right, perfect. Now let's print Xtest. So we'll get here 2 observations containing the same features here as here, right? This is the matrix of features still. So we have the dummy variables here in the first 3 columns, then the age and the 2 salaries of our 2 customers taken randomly from the dataset into this test set. Then Ytrain, so here we'll get 8 purchased decisions, right, with the 0s and 1s here that were encoded before with label encoder. And of course, make sure to understand this. These 8 purchased decisions correspond, of course, to the 8 same customers of this matrix of features Xtrain of the training set, right? These features correspond to these purchase decisions. These are the same customers here. And finally, Ytest, which will output 2 results, meaning 2 purchase decisions, right? 0 and 1, corresponding, of course, to the same customers as in this matrix of features of the test set. All right, so there you go. Congratulations. Now you have a new tool in your data preprocessing toolkit, splitting the data set into the training set and the test set. Not only you have this tool, but also you have the final answer to the ultimate question: do we have to apply feature scaling before or after the split? And it's clearly after the split to avoid indeed information leakage, because simply the test set is supposed to be something new, right? Something on which we evaluate our model on new observations. All right, great. So I'm glad that you are really making progress here with new tools and new knowledge that actually reduce any kind of confusion. So now we're going to move on to our final tool, right? Feature scaling, which now must be applied after the split, and you will see what we'll get with some other prints after we deploy this tool on our dataset. Okay, my friend, are you ready for the final tool of our data preprocessing toolkit, feature scaling, which will allow to put all our features on the same scale? So that's the what, and let me quickly remind the why. Why do we need to do this? Well, that's because for some of the machine learning models, that's in order to avoid some features to be dominated by other features in such a way that the dominated features are not even considered by the machine learning model. Now, you also need to be aware that we won't have to apply feature scaling for all the machine learning models, just for some of them. Therefore, we won't include this in our data preprocessing template, which I will show you, by the way, at the end of this tutorial. So we will just add this tool in the toolkit because indeed, for a lot of machine learning models, we won't even have to apply feature scaling, even if we have features taking very different values. For example, if you already know a bit about the multiple linear regression model, you know that each variable is actually multiplied by a coefficient, in the linear regression equation. And so, well, if you have variables that take much higher values than others, well, when learning the coefficients will just compensate by taking small values for the variables that take high values, right? We will explain this more in part 2 regression, but for now, just know that this is a tool that will be applied from time to time for certain machine learning models, but not all the time, as you will see in this course, all right? And also in the previous tutorial, I actually told you that I was about to answer one of the most important questions or most frequently asked questions by the data science community. And I will keep, of course, my promise. I will answer this when it's time, meaning at around the middle of this tutorial. But no worries, all questions about feature scaling will be answered so that you have absolutely no confusion. All right, so we have the what and the why, and now let's proceed to the how. Meaning, how are we going to apply feature scaling? And to answer this question, I'm going to show you the following slide, which are the main two feature scaling techniques that indeed put all your features in the same scale. And these two techniques are, first, standardization, which consists of subtracting each value of your feature by the mean of all the values of the feature and then dividing by the standard deviation, which is the square root of the variance. And this will put all the values of the feature between around -3 and +3, right? All the different features. When you apply this transformation on all the features of your dataset, well, all your features will take value between around -3 and +3. So that's standardization. And then you have normalization, which consists of subtracting each value of your feature by the minimum value of the feature and then dividing by the difference between the maximum value of the feature and the minimum value of the feature. And so, since this is positive, and this is always larger than this, well, that means that all the values of your features will become between 0 and 1. All right, so this will result in having values of features between -3 and +3, more or less, and this will result in having all the values of your features between 0 and 1. Now the question is, also much asked by the data science community, should we go for standardization or normalization? Well, we're going to be here very pragmatic. Normalization is recommended when you have a normal distribution in most of your features. This will be a great feature scaling technique in that case. Standardization actually works well all the time. It will do the job all the time. Therefore, since this is a technique that will work all the time, and this is a technique that is more recommended for some specific situations where you have most of your features following a normal distribution, then my ultimate recommendation for sure is to go for standardization. Because indeed, this will always work, you will always do some relevant feature scaling, and this will always improve the training process. So I'm going to teach you this technique. I'm going to teach you on how to apply it on our matrices of features. And I'm saying matrices of features because now we have two matrices of features, which are xtrain and xtest. And since we understood in the previous tutorial that feature scaling must be applied after the split, well, you understand that we won't apply feature scaling on the whole matrix of features x, but of course on both xtrain and xtest separately. And actually, the scaler will be fitted to only xtrain. And then we'll transform xtest, we'll apply feature scaling on xtest. Because indeed, since X-test is something that we're not supposed to have during the training, but only after, like when going in production, well, we're not allowed to fit our feature scaling tool on the test set, right? By fitting the feature scaling tool on the test set, that means that we're going to get the mean of the whole set and then the standard deviation in the feature. No, we don't have the right to do this because X-test is supposed to be something new, and therefore we'll just get the mean of the values in X-train, then get the standard deviation of the values in X-train, then apply this formula to transform all the values in X-train, and then apply that same formula but with the same mean and standard deviation of the values in X-train to scale the values of X-test. It's really, really important that you understand this, and this is once again to give some further elements of response to that previous question, should we scale before or after the split? All right, so now that we're all clear on this, let's proceed to the implementation of the how, meaning the implementation of feature scaling. All right, so as usual, in order to be as much efficient as we can, we're going to do this with scikit-learn, right? This data science library that has all the tools, and the tool that we're about to use is a class called standard scaler, and which will exactly perform standardization on both your matrix of features of the training set and the matrix of features of the test set. So let's do this. Let's start by importing this class, which we have to take first from, well, scikit-learn, of course, sklearn, and then from which we're going to get access to the pre-processing module, perfect, which is the module that contains that standard scaler class. All right? So then we're ready to import what we want, which is the standard scaler class. Perfect. So now we have the class, and then the natural next step here is, of course, to create an object of the class. I'm about to reveal soon that answer to one of the most frequent questions in the data science community. So let's create this object. We're going to call it SC for standard scaler. And then, well, this object will be created as an instance of the standard scaler class. So I'm taking it here, pasting that right here, adding some parentheses. And good news, here we don't have any arguments to input, because what we simply want to do is get that mean, get that standard deviation, and then apply this formula to all the values in the feature. And for this, we don't need actually any parameters. This will automatically do the job. All right, so then next step. And now, well, now is the time for me to reveal the answer to that question, which is one of the most frequently asked questions in the data science community. And that question is, do we have to apply feature scaling, standardization, to the dummy variables in the matrix of features? This is one of the most frequently asked questions. You will find it everywhere online as well. And once again, actually, the answer is pretty obvious, but only after you get the explanation. So let me tell you the answer. The answer is no. The answer is no because simply, well, remember the goal of standardization or feature scaling in general. It is to have all the values of the features in the same range. And since I told you that standardization actually transforms your features so that they take values between more or less -3 and +3, well, since here our dummy variables already take values between -3 and +3 because they're equal to either 1 or 0, well, there is nothing extra to be done here with standardization. And actually, standardization will only make it worse because indeed it will still transform these values between -3 and +3, but then you will totally lose the interpretation of these variables. In other words, you will lose the information of which country corresponds to the observation. Now we perfectly know that, remember 1, 0, and 0 corresponds to France because that's how it was encoded, and then 0, 0, and 1 corresponds to Spain. But after we apply feature scaling, if we apply it on the dummy variables, we will get nonsense numerical values and we will be absolutely incapable to say which tuple of 3 values here correspond to which country. So we will totally lose the interpretation, and besides, this won't improve at all the training performance because indeed our dummy variables are anyway already between the same scale range as your other variables. You will see online that applying standardization to your dummy variables might still increase slightly the performance, the final accuracy of your model, but I've experimented many times and I've never seen, a considerable difference that would justify here to apply feature scaling on the dummy variables. So really, don't do this. Only apply feature scaling to your numerical values, right? Here we have clearly some variables taking values in a very different range, right? The age goes between 0 and 100 and the salary goes between 0 and 100,000. So clearly here, if it's better for the machine learning model, we have to apply feature scaling, but let's leave these dummy variables alone so that we can keep the interpretability of the model. All right, so that was the other very important questions. Now I've covered everything. There should not be any confusion left in data preprocessing. I'm really glad that you know this, and therefore I encourage you now to press pause on this video and guess what will be the next step to apply feature scaling to our matrices of feature xtrain and xtest. All right, good. So now I'm going to give you the solution. So first of all, we're going to fit our scaler, our standardization tool, on the training set. So I'm taking the training set first, x train, all right? And then, since I've just explained that we won't apply feature scaling on the dummy variables, well then that means that we will fit our standard scaler object only on these two columns here containing the ages and the salaries. And therefore here, I'm going to take only the two columns here for the age and the salary, and then of course all the rows. And remember the trick to take all the rows, we just need to add a colon, which means we are taking the range from the lower bound to the upper bound, meaning everything. And then to take the columns, well, be careful. This is what we have to look at, not this, because indeed we want to take this column and this one. And so now the question is, what are the indexes of these columns? Well, remember that indexes in Python start from 0. So this has index 0, then the second column has index 1, index 2, and this one has index 3. The age column has index 3, and the salary column has index 4. But since I want to make this template as much generic as we can, and since when you one-hot encode your categorical variables, they always automatically go as the first column, well, we're going to do something even better. We're going to specify the indexes we want here by 3, which is the index of the age column, and then a simple colon, right? Because this will take the range from the column of index 3, which is the age, up to all the other columns. There is not the -1 here, so this will take all the remaining columns from the age, meaning the age and the salary. Basically, this will take these two columns, and if you have a larger matrix of features with numerical values in your features, well, this will just take all the columns. All right, so that's a little trick, more elegant, let's say. And so now we are, of course, going to use our object, which we called SC, from which, well, we're going to use that fit method that will indeed, for each feature of xtrain, compute the mean of the feature, meaning the mean of the age and then the mean of the salary, and then compute the standard deviation of the feature, the age and the salary. And that's exactly what the fit method will do. It will only compute the mean and the standard deviation of all the values. And then you have the transform method that will indeed apply this formula by, transforming each of the values here of each feature into this value resulting from this formula. All right, so it's important to understand the difference between fit and transform. Fit will just get the mean and standard deviation of each of your features, and transform will apply this formula to indeed transform your values so that they can all be in the same scale. All right, and now the good news is that one of the methods of the standard scaler class is actually fit transform, which of course will proceed to the two tools at the same time, meaning it will fit your matrix of features to get the mean and the standard deviation, and then right after that, transform all the values of the features to turn them into this formula. All right, so let's call this method right away to make it efficient, fit underscore transform, then some parentheses, and now obviously you know what to input inside this fit transform method. Well, that's of course exactly the same as xtrain here, because indeed we will only apply feature scaling to our numerical columns here containing non-integer values, right? Non-dummy variables values. All right, great. So this will apply feature scaling to our two columns of the training set. And now I hope you know what the next step is going to be and you won't fall into the trap. Now we have to also transform our matrix of features of the test set, meaning xtest, this matrix of features. But since this data is like new data, which we get, later on in production, well, for this data, we will only apply the transform method because indeed the features of the test set need to be scaled by the same scaler that was used on the training set. We cannot get a new scaler. If we apply the fit transform method here on xtest, we would get a new scaler. And that would absolutely not make sense because xtest will actually be the input of the predict function that will return the predictions, after the machine learning model is trained. And since this machine learning model will be trained with a particular scaler, the scaler applied on the training set, well, in order to make predictions that will be congruent with the way the model was trained, well, we need to apply the same scaler that was used on the training set onto the test set so that we can get indeed the same transformation and therefore, in the end, some relevant predictions with the predict method applied to xtest. So here, it's clearly the transform method that must only be applied, and therefore, what we're going to do to make it efficient, well, we're going to copy this line of code, and just below we're going to paste it. We're going to replace, of course, xtrain by xtest, and then here as well, xtrain by xtest, and then just call, of course, the transform method from that same scaler that was applied on the training set, because indeed this is part of the training, right? Even if we haven't started the training, well, this operation that we apply here on our training set is, the preparation of the training. All right, so I hope it's clear. It's very important that you understand this. And now, well, I have to say congratulations because we're actually done implementing our final tool. And of course, I'm going to show you the result of feature scaling here. So let me create 2 more code cells inside which we're gonna print first x train, and then let me copy this, and then we're gonna print x test. All right, perfect. So let's first run this to apply feature scaling. Perfect, there we go, no execution error. Then let's print x train. And of course, we get, well, still the same values for the dummy variables, which are indeed still between -3 and +3. But then our age and salary variables were transformed so that they take new values between -2 and +2. Sometimes you will see values between -3 and +3. Here it's -2 and +2. But anyway, now all our variables are on the same scale, and this will be perfect to improve or optimize the training of certain machine learning models. And of course, you will see exactly which ones they're going to be the further we progress in this machine learning course. So now you know everything. Let's also execute this cell to print xtest. And once again, well, you still have your dummy variables here for the same 2 customers that were here, but then the age and the salary were scaled so that they take, once again, values between -2 and +2. All right. Okay, so great. I'm really happy that we're now done with this data preprocessing toolkit because that means only one thing. That means that we're ready to start the exciting steps of the journey, which is to build machine learning models that will perform amazing predictions. And we're going to start with the regression models, which will predict some continuous numerical values, and we will learn how to do that on different data sets. But before we move on to this next part, I just want to show you the data preprocessing template, which will be so useful for us to tackle in the flashlight the data preprocessing phase for each of our future machine learning models, because indeed you will see that this template was made so that we will only have each time 1 or 2 things to change, and most of the time 1 thing to change, because indeed in this template I included the 3 always used tools that we will use for our machine learning models, which are importing the libraries, right? We will always need these libraries, then importing the dataset, and here appreciate that we will only have 1 thing to change, which will be the name of the dataset, because indeed this line of code will automatically take all the columns except the last one, meaning all your features, and this line of code will take automatically the dependent variable. So here you will only have the name of the dataset to change, and then of course I included this tool because for most of our machine learning models we will have to split the dataset into these 2 separate sets, 1 training set to train our machine learning model and 1 test set to evaluate its performance. And here once again we will actually have nothing to change. So in the whole template we will only have one thing to change, which will be the name of the dataset. And that's why this data preprocessing template will be so useful for us, because we will each time tackle the data preprocessing phase in Flashlight. So make sure to have this template ready each time we're going to build our future machine learning models. And now take a good break. You really deserve it after this data preprocessing phase and these answers to the questions that reduce any confusion. So digest it well, and as soon as you're ready to tackle the first branch of machine learning model, which is regression, well, let's continue our journey together in this next part. And until then, enjoy machine learning.